We've already found when it's decreasing and when it's increasing. And so now we want to talk about concavity. Concavity is looking at the slope function. When is the slope function positive? When is the slope function negative? And we're looking at when it changes. Well, when the second, so we're looking at the second derivative, and we have what we call inflection points when the second derivative equals 0. That will mark when our slope function is changed from positive to negative or negative to positive. So we come over here to our function, and I'm going to focus on this one here, and I'm going to find my second derivative, which is 12x squared minus 30x plus 18. And again, if I factor this, I can factor out a 6, and then I'm left with 2x squared minus 5x plus 3. And now that factor is really nice for me into 2x minus 3 and x minus 1. Now that's going to let me know that my inflection points that's when the second derivative equals 0, are when x equals 1 and x equals 3 halves, or 1.5. Okay, so now again I can look at my number line here again, and the way I can look at this is if I bring a text box down here, I can manipulate this, so just give me a moment. So if I think about my number line and say this is 1, and I'm going to make it a little bigger so it's easier to work, and this is 3 halves. Then I'm looking at these intervals here, there should be 3 of them, since I have 2 inflection points, to see whether they're positive or negative. So if I look over here, I am looking, okay, let's pick a number to the left of 1, such as 0, and 6 is always positive, so I have a positive. Put 0 in here and I get a negative. Put 0 in here and I get a negative. So I know that this whole area is positive. So if it's positive, it's concave up. So we can conclude that when the second derivative is greater than 0, then it is concave up. Okay? And so that means that it's concave up on the interval. Let me just create some more space up here. On the interval from negative infinity to 1. Now, if I try an interval in here, right there, so 5/4 is going to be a good number to try. And if I try 5/4, then I know that I'm going to have my positive times 5/4. Well, that's 5 halves or 2 1/2, so I know that's negative. And if I put 5/4 here, I know it's a little more than 1, and that's positive. So I know that whole thing is negative. So when the second derivative of x is less than 0, we know it's going to be concave down. And so we're able to say, okay, from 1 to 3 halves, it is concave down. So probably some of you have figured out that when we look at these things, often the concavity changes. So you'd probably say, okay, well, this one's going to have to be positive. But let's check it by picking a number that's to the right of 3 halves, such as 2. And if I put 2 in there, Remember, 6 is always going to be positive. Put 2 here, and I get 4 minus 3, or a positive number. And I put 2 in there, I get a positive number, and lo and behold, it's always positive. So it's concave up. So we say it's also concave up from 3/2 to positive infinity. Okay. We've also answered question E, which says what are the values in which the x values of the inflection points, and that is when x equals 1 and x equals 3/2. As we build in this chapter, we're going to start looking at what this picture actually looks like, because it's going to give us more detail than we get on our calculators. All right, I hope that helps. This is question 20 again on page 242.